can go upstairs and go outside and take a look through the scopes. I think we're going to have Mars, Jupiter, Saturn, Moon, so it should be great. Tonight's speaker is Dr. Jillian Bellovary. She's the Helen Postdoctoral Fellow at the American Museum of Natural History, Department of Astrophysics. She studies black hole growth. But tonight, can you feel it? Yeah, I didn't. So anyone who felt that. But there are gravity waves passing through us right now, and our speaker will tell us about that. And in addition, well, she also teaches the STEM education program for high school girls. But more than anything else, I'm sure she would want me to tell you all to support your local roller derby. Get out of here! Don't do that! I didn't even realize. Give her a hand, please.
Thank you, John. Thank you, everyone, for coming. It's fantastic to be here. It was such a packed house. This is really great. So, how many of you folks have heard about these gravitational waves in the news? Give me a hand. How many of you have a clue what they're about? All right, that's not too bad. How many of you would like to have a clue of what they're about? Okay, cool. Because they're super weird. You have to get your imagination out of your pocket and have it readily accessible right now, because this isn't normal sensory experience. This is cool, weird stuff. All right, if your imagination is lost, then I'm sorry for you. You need to go and find it. So we're going to talk about gravitational waves, also known as ripples in space-time, which happens when black holes merge, and also how do we observe this? How do we know what these are? So before we start talking about gravitational waves, let's talk a little bit about space-time. I called them ripples in space-time. Well, what is space-time? So space-time is sort of the fabric of the universe. We know what space is, we know what time is, but time and space actually meld together in this sort of four-dimensional soup. So you can sort of think of space-time in a two-dimensional analogy as like a rubber sheet. And if you put a bowling ball on a rubber sheet, the rubber sheet will sink and you'll make sort of a pit where your bowling ball is. Yeah. But if you put like a golf ball on your rubber sheet, it would be just like a little small divot or maybe nothing at all. So the heavier the thing is, the more of a dip you get. So space-time is kind of like our rubber sheet. And if you set the sun on the rubber sheet, it makes a divot. And if you set a neutron star, which is something that forms after a massive star explodes, you get a deeper one. And if you have a black hole, which is another thing that forms when a massive star explodes, but even a more massive star, then you get a really deep one. And so you can see that far away from where we've set our bowling ball things, these lines are sort of straight, like they're normal. Things far away from where we've put our bowling ball are normal. But when we get close to it, these lines start to warp and bend and curve. And that's where space starts to warp and bend and curve around these massive objects. And so when you have massive objects moving through space, they take that warp with them. And this curvy warp space rubber sheet bent thing moves around in space. And when two of these come together, they really mess things up. It's a huge mess. It's a really great mess. Cool. So that's what space-time is. It's basically bending space around. And when space bends, it means that when you travel through space, your path also bends. So if you have space that's bent in a circle and you shine a flashlight into it, your light will travel in a circle. Crazy. Isn't that crazy? Yes, that is crazy. Okay. That's kind of my explanation of space-time. And a gravitational wave travels through space-time sort of like water droplets in a puddle. So if you look at this little animation here of a droplet in a puddle, you can see the waves sort of propagating outwards, rippling over the surface of the water. And that's a good analogy for the rippling of gravitational waves through space. except that instead of the water moving, like it is here, which makes sense, we can see water moving with our eyes, we understand it, space is moving, which we don't experience directly, so we don't understand that. So if a gravitational wave travels through us, it stretches and squishes space. So if I'm a regular sized person and a gravitational wave passes through me in a vertical way, I get taller and shorter and taller and shorter. Or if it passes through me like this kind of way, I can get skinnier and fatter and skinnier and fatter. But I'm not like really getting skinnier and fatter. I'm not like eating a lot and then getting really skinny, because it's happening all in one moment. Can I have a demonstration, friend? Will you stand up, please? What's your name? Joseph. So Joseph and I are standing like 3 feet apart right now. And we're hanging out and we're talking. Hey, Joseph, what's up? Hey. And a gravitational wave comes through us. Joseph and I move further apart and then closer together, and further apart and then closer together. But we're also just standing here. Like, we're just standing here. And that means space is stretching and squishing. If we had a yardstick here, that yardstick would also be stretching and squishing and stretching and squishing. So we would always be 1 yard apart because the yard is changing. And so 1 yard gets long. It's still 1 yard, it's just long. And then it gets short, and it's still a yard. It's super weird. Thank you, Joseph. You may sit. So space changes size and shape. It's crazy. But it means we can't measure this with a yardstick, because our yardstick also changes. So what do we do? All right, moving on. Here is a video. This is a dramatic exaggeration. This is not what happens. But if we make an animation of gravitational waves passing through the Earth, there are these green whooshes. See how Earth is starting to wiggle a little bit and gets wigglier as more and more of them happen? That totally does not happen when gravitational waves actually pass through the Earth. Maybe if a black hole merged like right next to us, that could be bad for lots of reasons. But that's sort of a cartoon of what it's like when gravitational waves pass through something. All right, so what kinds of things emit these gravitational waves? Where do they come from? Like, what are they from? So orbiting and merging compact objects will emit them. So what does that mean? Well, black holes, if they're orbiting each other and they merge, they'll emit gravitational waves. If you have a black hole and a neutron star and a moth, they will also do that. Remember, neutron stars and black holes are both the remnants of massive exploding stars. 2 neutron stars will also emit gravitational waves if they merge together. What else? Supernovae are how these neutron stars and black holes form. They will emit gravitational waves too. The Big Bang also emitted gravitational waves a really long time ago. And question marks emit gravitational waves. That means there's probably stuff that we don't know about that also emits them, but maybe we'll figure it out. Did you have a question?
Well, just that you're saying that they emit gravitational waves when they're emerging. Aren't they always emitting gravitational waves? It's just that they're too small to measure.
That's true, is that they're not quite always, but once they get to a certain distance, they start emitting gravitational waves as they get closer and closer together, yes. And then the amplitude gets larger and larger, and the frequency gets shorter and shorter as the merger happens. And we'll see that happening as I go into the talk. So good question. Are there any other questions? Besides that I should stand over here instead. Fine. Okay, so compact objects merging, supernova, Big Bang, question marks, maybe other stuff. So how do we observe them? We can't feel them. Not helpful. We can't use a ruler. I already explained how our ruler changes size along with the space, and that's not helpful. We definitely cannot use a telescope. This building is full of telescopes. None of them can see gravitational waves. They're not made of light. Telescopes see light. Light is cool, not here. So what we need to do is build a machine that feels these ripples in space-time. And here is a hint. Light is still useful to us because it is impervious to changes in space-time because it always travels at the same speed. That's something Einstein figured out back in the day. Light always travels at the same speed no matter what it's really doing. And so even if space-time is warping and changing and doing weird stuff, light speed is always constant. So that is how we start to build our contraption. So when in doubt, we use lasers, because lasers are cool. So when light has this property that it is like a wave, so you can see that in this little picture. When the waves of the light line up together, they actually add together and make each other taller. Bless you. And that's something that is called constructive interference. Basically, you get two waves that are together, you can make a bigger wave. Okay? It's like if you have two snowballs, you can put them together and make a bigger snowball. Snowball would be awesome right now. It's like a zillion degrees out. On the other hand, if your waves are lined up opposite each other, they cancel each other out, and you get a nothing. This is called destructive interference. So these waves can interfere with each other depending on how the up and down parts of the wave are lined up. Good? Okay, so we use this interfering thing to build an interferometer. It's not called an interferometer, it's an interferometer, but it basically measures the interfering of light. And so it has this sort of cross shape, and basically you have a laser, and your laser sends light this way, and it sends light this way, and it bounces off, and it all comes together here, and this thing measures whether or not the patterns are in phase or out of phase, or if they're matched up, or if they're canceling each other out. So if they're canceling each other out, you get nothing. If they're in phase, you get this cool pattern thing. So this is something that if you take a high school or college physics class, you get to play around with this kind of thing. But what we need to do to measure gravity waves is to build an enormous one. And this thing is called LIGO, the Laser Interferometer Gravitational Observatory. So it looks like this. There's two of them. So remember how an interferometer has this cross shape? Here is that big cross shape, but it's on the plains of eastern Washington in Hanford, and it's in the swamp forest of Livingston, Louisiana. These arms are 4 kilometers long each. That's like 2.5 miles. It's pretty long. So this is a really, really big interferometer. It's huge, and it needs to be huge because of the frequency that the gravitational waves have needs to be correlated with the size of the thing you're using to measure it with. And so the frequency means that the waves are really, really long, and so you need something really, really long to measure it. So we have two of these, one in Washington and one in Louisiana. And these are what measure our waves. So how do they do it? So let's play the movie. The idea is that there's an interferometer, but these things, instead of being mirrors, are actually hanging mass pendulum things. So we'll do a journey through the interferometer. The laser goes down to the thing. It bounces off the thing. They come back and they join each other and go to the detector. So this is measuring the pattern. And when these guys move back and forth, which they're going to do now, see how they're wiggling? The pattern changes. So if a gravitational wave comes through and makes these hanging masses wiggle around, we see a change in the pattern of the light over here. And that is how this thing works. And so what are these hanging masses? Well, you can't just have a mass like with a mirror on it that's hanging there, because it needs to be really, really sensitive. And so you actually make this quadruple pendulum thing where you have, here's your thing that wiggles back and forth, and it's hanging from another thing, which is hanging from another thing, which is hanging from another thing. So there's all these things that are all there, but what that means is that it only wiggles if a really, really sensitive thing happens. And when that happens, this will wiggle in a particular way. So you have to have it be really, really sensitive. So for example, there are earthquakes on the planet. You can't build one of these in a place where there are earthquakes, although there is one in Washington. There are earthquakes in Washington. That's partly why we have more than one. There's an earthquake in Washington. We won't feel it in Louisiana. So we know that it wasn't a gravitational wave. It was an earthquake. The pounding waves from the ocean cause these to wiggle. Other seismic events cause it to wiggle. In one case, a truck drove into one of these. That was bad. I think everyone was okay and didn't wreck anything too badly, but that made it wiggle. So, so you have to basically measure everything really carefully and also learn how to subtract all of the regular life things that make the Earth wiggle so that you can figure out those astronomical things that are making it wiggle. It's very hard. Any questions so far about this stuff? Yes, Joseph.
How far can the legal measure?
How far can it measure? It can measure to about 400 kiloparsecs, I think.
What are parsecs?
We'll have to talk later about that. Yes?
What if you do to put it in space?
My very last slide is putting it in space. You have to be patient and wait, but I will answer your question later.
Oh.
Okay, you're jumping too far ahead. You are too much imagination. Good for you. Any other questions before I go on? Okay, all right. So the LIGO detector needs to be extremely precise. So, for example, if we are measuring the distance from the sun to the nearest star, we would need to measure it to the precision of the width of a human hair. That's crazy. Guys, that's crazy. It's to be so precise. The real measurement that it makes is, the measurement that it made when it made its first detection was the size of a fraction of the diameter of a proton, which is really, really small. It's almost as small as we can wrap our brains around. So we have to have a really sensitive detector. So what did it see? So in September, there was a measurement of gravitational waves. It was not announced until January because it took them a really long time to be really, really sure of exactly what it was. But they're really, really sure. It was definitely two merging black holes. And so here's what a detection looks like. A detection is a squiggly line. And what this line means is this axis here, the vertical axis, is the amount that the detector moves. It's basically how much does it wiggle. So it wiggles a little bit, and this is time on the x-axis here. So as time goes by, it wiggles a little bit, and then it starts to wiggle more, and then the wiggles get really tall and skinny, and then they flatten out again. So the Hanford, Washington detector saw this wiggle, and the Livingston, Louisiana detector saw the same wiggle. That's a good sign. Thumbs up to that. Also cool is that the people who do calculations about merging black holes came up with a calculation that pretty much exactly matched these wiggles. So you can see these lines on the bottom that are a little smoother, but they're still kind of the same. That is the theoretical calculation that exactly matches. That's how we figure out what is going on. That's how we translate a bunch of wiggles into this black hole did this, and that black hole did this, and then they did this other thing, and then they merged and blah, blah, blah. That's what this squiggle means on the bottom. And so the one in Louisiana actually saw it first by a little bit. And so from that, we know that the merger happened closer to Louisiana than to Washington. But it's still hard to tell quite where it happened. And so I think I'm hooked up to the sound. But we can hear the frequency of the gravitational wave detection with our ears. We can't hear the gravitational waves. They don't make any sound. They're silent. But the frequency that they travel with is the same frequency that sound travels with that we can hear. And so there's this little movie that was made. Do you hear that? So what is that? So the first sound is the real frequency translated into sound of the gravitational wave. And this little picture here, can I play it again? this picture is time and frequency. And so the frequency increases over time, and that's why we hear it kind of going whoop, whoop. That's the frequency increasing over time. And the second one, so it plays twice at the normal pitch, and then it plays twice at a higher pitch, and the higher pitch is just adjusted so that we can hear it a little better. That's all that is. So I'll play it one more time. Cool. So if we had gravity ears, gravitational waves would sound like that. All right, cool. Here is another movie that's more of a visualization. So here, the black hole environment has been translated into this kind of rainbow space-time. So because we can't see gravitational waves, we've basically told all the artists we know to try and make ways to visualize gravitational waves. So the space-time when it's normal is blue, and then when it's getting really stretched and distorted, it turns into these rainbow colors. And the black holes are sort of hovering above the space-time just so you can see where they are. And so you can see these big pits, which are the warped space-time underneath the black holes. And the black holes are orbiting and getting closer and closer. So those pits are getting closer and closer. This is slowed way down. And then they freeze the movie when it gets super crazy. The black holes are about to merge, and space-time is like doing crazy gymnastics, backbend things. And then they merge. The movie's frozen. And then space-time is like, oh, and sort of sloshes back into its normal configuration for just one black hole, because now there's just one. And so now it looks kind of like your raindrop in the puddle. So there we are. So that's, I didn't make that. the LIGO people made that, and they are very good at making those things. But that's really cool, right? Yeah.
Who are the LIGO?
There's a team at Caltech, and there's a team in Louisiana, and there's a lot of other people everywhere. There's about 1,000 people in the collaboration. So every time they publish a new article, there are 1,000 names on it. There's like 5 pages of names before the article starts. You learn to skip those pages. And they're also all alphabetical in order. And so one guy whose name is Abbott just gets to be like at the top of the list every time because his name is Abbott. There's 3 Abbotts, so like B Abbott beats D Abbott and K Abbott or something like that. Yeah, there's a lot of people. Yeah.
So 2 black holes take 1 second to merge?
They-
I thought it was a really slow process that took like a million years.
So it does take a very long time for black holes to merge, and the part of it that is in the frequency range that we can detect was less than a second. So the merger that takes a million years is really, really slow, and the frequency is too low for LIGO to detect. And so LIGO does not know about that part of the event.
Where are those 2? How far away?
They are less than, if they're stellar mass black holes, I'm not sure. I think about supermassive black holes a lot, and those are a parsec or less apart. The stellar mass black holes are closer because their masses are lower. I'm not actually sure.
How far compared to our sun are they from us?
Oh, how far away in space are they?
Yeah.
There's a lot of them all over. None of them are real close. Yeah. Yes.
Is there any way to measure the distance to the merger for Earth?
Yes. That is here on this slide.
Oh, okay.
Good question. Good segue. So here's the fact sheet for that first gravitational wave event. These 2 black holes had masses of 36 and 29 times the mass of the sun. So those are pretty big. Those are actually kind of weird masses. I could talk about that at the end if you want. But that was a surprise. When they merge together, they are 62 times the mass of the sun. But notice, if you want to math real quick in your head, 36 plus 29 does not equal 62. That math is wrong. So what happened? It turns out that some of this energy is actually radiated away in gravitational waves. That's actually how the stuff merges, is that it gets closer together because it's losing energy, because the gravitational waves are carrying energy away, and that energy basically takes the mass from the black holes and is converted into energy, because E equals mc squared, Einstein. Do you have a question? Yep, the energy is that E and the mass is that m, and it's exactly that. Yep. So some of that energy is radiated away. This merger happened 1.3 billion years ago. That means it was really far away, and it's taken 1.3 billion years for that light, or that, not light, there's no light, those waves to reach us. So 1.3 billion light years is the distance to these black holes that merged, which is really far. That's not in our galaxy. That's in some other galaxy way over there, far away. We did confirm that the speed of light is equal to the speed of gravity, which we thought was pretty sure. I mean, Einstein was like, yeah, these speeds, they're the same. But now we know it's totally true. And the detection was really, really strong. So we measured detection with something called a signal-to-noise ratio. And if your signal-to-noise ratio is high, that means you really detected something really, really loud, because you can hear it above all of the background noise. And so this was a really giant detection. It was huge, and it was the first one, and it happened like a day after they turned the thing on. They were like, all right, our upgrade is finished. Our stuff is all ready to go. Let's turn it on. And the next day, like, bam, and they were like, oh crap, now what? What was that? Which is why it took them like 4 months to be like, okay, we saw the thing. And it turned out during that time there was another one. So this one happened. It was actually Christmas Day here, although we measure things in Greenwich Mean Time in astronomy, and so we call it the Boxing Day event, because Boxing Day is the day after Christmas Day. But it turned out that there was another one that happened, and they didn't announce this one until June, and so they're getting better at announcing as they go. But the second event was 2 black holes again, but they were smaller, 8 and 14 times the mass of the sun. And this one, because they're smaller, we could actually observe more of the in-spiral. So you were asking, why doesn't it take a long time? Don't we see more of it? And this one, we could actually observe more of it. We could observe 27 of their orbits before they merged. And that took 1 second for that to happen. And I'm going to get out of this and show you YouTube in a second, and then I'll show you that. Yeah?
Do you have the time that it happened or the distance away from us first in order to find the other one? Like, how do you know how far away it is first, or do you know?
No, you know the time first. You figure out how far away it is later. You figure out how far away it is by comparing to different models, different general relativistic models of different merging objects.
Figure out how many years ago it was?
That's related to the distance. The distance tells you how many years ago it was.
Which one
Because
came first?
they're the same thing. Because it travels at the speed of light. The waves travel at the speed of light, and so since you know they're always traveling at the same speed, if you know distance, you know time.
Oh, right, okay.
All right. I want to muck around with a computer and open up YouTube. I'm going to do that. Let's see. But my mouse is over here. Okay. Dun, dun. Make you big. All right. So this is the comparison of the 2 events. So you can see how they're a little different. This is the increased pitch. So this one is longer. I'll play it one more time. So the new one is the first one that they play. No, really. What do you, no. Don't need that guy. Okay. So here's the new one. So it lasts for a whole second, and that one is much shorter. And it's because the masses are smaller, so we can detect them sooner. Cool. You can download that for your phone ringtone and stuff too. I have done it. All right. So that's a way to compare them. And I want you to be big and you to you Windows computer. You were going to go from the beginning, aren't you? Okay. So are there any questions while I fast forward through my whole talk? Yes?
You had on the slide one of the black holes was spinning. What? Yes.
Yes.
Yeah. What does that mean? Aren't they always spinning?
Yes. So do black holes spin? Yes, they probably all spin, but measuring their spin is hard. We think they spin just because everything in space is spinning at least a little bit. So black holes probably are too, because it would be weird if they weren't. But with this detection, we could actually measure the spin of one of them, which is cool. Because then, we knew it was spinning anyway, but now we can measure it. There's a difference between doing this and doing this. And it was doing the second one, basically. So that was cool too. So we can measure distances, we can measure masses, we can measure spins. It turns out that I think there are more detected than just these two. But remember how the collaboration takes like 4 months to announce anything? So I think they're still sitting on some more. I think they're doing the math and they're trying to figure out, is this really a thing? Maybe it's this other thing. What's really going on? We don't know. What is that? So I think there are more. We'll have to see, because I don't actually know. It's just a suspicion I have. Yes?
Wasn't there a series of interferometers prior to LIGO that just never detected anything? It took a while to build one large enough?
There's been a series of LIGOs. The idea happened in like the 60s, and they got funding in like the 90s, and they built it in the 2000s, and then it didn't detect anything at all. And then we were like, well, that was a waste of millions of dollars of taxpayer money. And then they're like, but no, wait, we need to make it better. And they convinced Congress to give them more money, but they were right. They made it better. And so there's been a lot of stages of making it better, and they're not actually done making it better. It's been the same facility the whole time.
And there's a new one in Europe or someplace that's going to be larger?
Yes. So we'll get to that in one more slide. So something that LIGO is bad at is figuring out where in the sky it is. Like something you might want to do tonight would be like, oh, so now that Jillian's done talking, let's use a telescope and go look where the thing was. We don't know where the thing was. So here's an example of a map of the sky. You can imagine like if you had a map of the Earth, you were seeing part of the Earth, it would be like this. And these sort of rainbow contours are where we think the objects maybe sort of were. So we have this sort of skinny oval for this first one, and we have a way bigger stripe area maybe for this second one. But this is like across the whole sky. So like you could look in this stripe across the whole sky and look for something, but you don't know where it is. And that's because there are only 2 of these detectors. But with more of them, we can figure out more stuff. So here's the future of gravitational wave detection. So the 2 that we have are these guys here. And this one, Virgo in Italy, is coming online next fall. And it's the same as these other ones. It's not bigger, but it's more sensitive. So that's fine. But it's the same size. But the fact that there are 3 in this triangle now will actually really help us figure out where in space stuff is coming from. There's one in Japan that will be built a little bit later. And the government in India just approved funding to build one in India as well, which is awesome. There's going to be things all over. Oh, and this one is small. It doesn't do anything, so ignore that. doesn't do it. Maybe if there was something giant, it would see it, but it doesn't detect anything. So we're going to have a whole array of them around the planet. Remember our wiggly planet from the beginning of the talk? When the planet wiggles, there'll be detectors all around the planet that will see it, which is super cool. But what about your question? What if we could put one in space? That would be amazing. Anything in space is amazing, right? It's because it's in space. So the future of gravitational wave detection is the same kind of L-shaped interferometer, but in space. This is called ELISA, and is being built by the European Space Agency, but NASA is going to help because we all help each other out, because this stuff costs $1 zillion, and we can't build it if we don't help each other out. And this kind of a detector, because it is in space, it can be bigger. See how it's like way bigger than the Earth? It is way bigger than the Earth. It's actually big. The moon is like maybe right here. It's not on here, but it's like this far away in this picture. So like it's bigger than the distance between the Earth and the moon. And there's going to be 3 of these detector masses, and they're going to wiggle back and forth, just like the ones on Earth, but they're going to be enormous. And what does that mean? How is that different? It means they can detect a different type of gravitational wave event. It means they can detect things like supermassive black holes instead of stellar mass black holes. So the black holes we've been talking about are like 10 to 30 times the mass of the sun. Supermassive black holes are like 1 million to 1 billion times the mass of the sun. I don't know what I just did. So there's a whole nother like family of black hole types in the universe that LIGO will never see, just because when they merge, the frequencies aren't the right kind of thing for LIGO to see. And that's because the arms aren't the right size. But these arms are for supermassive black holes, which are my thing. Well, really all the kinds of black holes are my thing, but the supermassive ones are totally my thing. And so this is going to launch in 2034, which is not soon. But there is a mission called the Lisa Pathfinder that went up this year, which is basically just one of these, just to test, like, is this technology even going to work at all? Like, if we put this thing in space, is it going to do what we think it's going to do? And it turns out it does. It does it better than we thought. So that part is cool. We're good with technology. We just need to figure out how to get these to stay in the space they're supposed to stay in, and some other stuff. That's all really, I'm not an engineer, I don't do that. Engineers do that. But that's the other future of gravitational wave detection. And so with that, I will end with, why should you care about this? I mean, we can't even see these, but you should care because for the first time ever, we can get information from the universe that is not made of light. We have information of a totally different kind. And we can use that with information from light to learn about the universe. And we can probably discover whole new things we didn't even know about because they don't make any light. If you don't make any light, how do we even know about you? We have to make a bunch of guesses. We have to figure stuff out. But if we can detect gravitational waves, we can be like, oh, there's a thing over there. What is it? I don't know. But why don't we try and figure it out? And then we do our science, and we discover new things, and we learn about the universe, and it's really cool. It's so cool. So with that, I shall let you explore the sky. I hope it's clear out. Have a great night. I'll take questions.
Are there any questions before everybody leaves, please?
All right, we'll go you and then you. Yep.
So do stars orbit around the galaxy, around the center of a galaxy, because the supermassive black holes inside them spin?
The stars orbit around the center of the galaxy, not really much because of the supermassive black hole, but because of everything that's in the center of the galaxy. So the supermassive black hole is definitely the heaviest thing, but there's way more other stuff that together is heavier, and so it's the gravity of everything put together that makes everything go
So
around.
could the black hole start the chain, affect what's just around it, and that's going to affect everything around that?
It's probably not the thing that started it spinning, because as everything forms, it's all moving around and it just kind of starts to naturally spin. We think black holes spin when they either merge with other black holes and change their spin, or if they eat a whole bunch of gas that's also spinning, then they can spin along with it. But it might not be related to any of the stars around it at all. Some of them we think are spinning at like some funny angle with respect to all the stars. Crazy. Yeah.
How do they determine the distance to this event? With light, you have the shift that allows you to figure it out. How do they do it? Is there a shift in gravity waves?
The gravity waves are also redshifted, just like in optical light waves. They figure out I think they figure out the distance by when they make the model of the smooth line and they match it to the detection. The distance to it is part of the parameters that they do to make the theoretical line, and so they have to match all of the parameters all together at once, and then the distance comes out of it that way.
Are there any other questions?
Yes.
So, if that happened 1.3 billion years ago, that wave has been traveling for 1.3 billion years. And in that time, there must have been hundreds or thousands or millions of other events. Do they not overlap and interfere with one another and make them difficult to detect?
I believe they do overlap and interfere with each other in the same way that light does. But as light travels through, light is interfering with each other as it goes through the universe, and we can still detect it. And so we can detect things as long as they're bright enough, basically. If you're bright enough, if you're not faint, then enough gets through that, or you have just a big enough amplitude of your signal that we can detect it. And so these gravitational waves are really strong, even though they're pretty far away, and so they probably are crossing some other waves. And that's probably what some of the extra wiggles in the signal was. The signal is kind of hairy, and so part of it could be from that.
Because it must be detecting hundreds of these events at any given time.
Right, but they're too low level for us to see, and so maybe there's some sort of background level that we don't have any way to characterize that, though. It's very difficult because our machine is now very, very sensitive, but it can still only detect like the really biggest things. Yes?
For the first wave, you described the magnitude of it as being 24. I forget what you called it, but it's essentially...
Signal to noise.
Signal to noise. What was the signal to noise for the second one?
Oh, it was much lower. Something like 8, maybe? I'm not sure. Don't quote me on that. The internet will know.
But it was less.
It was definitely less. There's a picture I had of... Did I have it? So above here, I mean, it's small, but remember how the wiggles for the first one were really obvious and crisp and clear? This one is really hairy. Like, this is the second detection in the wiggle versus time, and it's a mess. Like, with your eye, you can't see that there's a detection there. You can only tell that it's there with math. So the signal to noise is much lower. Yes?
When you guys are done with all of the research, what would be the end goal? Like, what would be to come from this?
That is a great question. He asked, when you're done with all the research, what is the end goal? I don't know how to answer it because we're never done. There's always more questions to ask in science, whether it's astronomy or biology or anything. Like, you can never know everything. And so there's always more things that you don't understand. There's always more things to figure out. And so the research is never really done. But the goal is to try and figure out how many black holes merge, how often does it happen, where does it happen, how big are they when they do merge, are they spinning? We also want to learn about neutron stars and other objects. We can learn about supernova. So it's not just even black holes. There's so much we can learn with gravitational waves. And so we will never run out of questions. Which is why I think science is really awesome, because I will always have a job. Yeah, in the back.
I don't know if you mentioned this before, but do you guys know if black holes actually spit out matter or suck in?
They don't spit or suck. They're much more polite than that. So things can fall in to black holes, and when things fall in, they actually glow a lot, and they can be twisted around, and there are magnetic fields going all around the black hole, and so they can actually be shot off in different directions. So sometimes you see these jets coming out of a black hole, and they're not actually coming out of the black hole, because once something goes into the black hole, it doesn't ever come out again. But the stuff that looks like it's coming out is actually like right next to the black hole, but then gets like whipped around and shot out in some other way by all of the crazy stuff that's going on.
So the black holes themselves aren't visible, but the other stuff that's going on right around it is visible.
Yeah, so and that's how what's one of the main ways that we figure out if a black hole is around is because we see like a bunch of X-rays coming out of nothing. Well, nothing doesn't make X-rays, and so there's probably a black hole making those X-rays, and then we look further on and we can see, oh yes, there's gas and it's moving and it's doing this stuff, and it makes sense it's a black hole. Mm-hmm. Yes?
Yeah, how far would a gravitational wave propagate before it dissipates? Or does it ever dissipate?
It dissipates as it propagates, so it gets fainter and fainter with an inverse square relation of the distance, just like any gravitational or light thing. And so mathematically, it never really stops. Like if we were to go up in a spaceship and leave Earth, and we go up and we're weightless in space, we're technically still feeling Earth's gravity a little bit, and if we go way, way further away, we say, okay, we're not feeling it anymore. Technically, we never really leave Earth's gravity because every single thing in the whole universe is exerting some tiny amount of gravity on us. Even we have gravity between us because we are made of things. We are made of stuff. We have mass. But the forces just get so small that we don't care about them anymore. But the gravitational waves will technically keep going forever, just like light will keep going forever.
So the wavelength stays the same, just the amplitude reduces over time?
Yeah. Yes. Was there another question next to?
What do you think? Early universe, more of these, or late universe, more of these?
Ooh, both. Yes, I don't know. Early universe, probably a lot. I think it depends. So we don't really know how they form. Black hole binaries are not trivial to form. I'm actually working on a project that's thinking of a new way to form binary black holes next to supermassive black holes, which is a really neat idea that people haven't thought of a lot. We're still trying to model it to see if it's true or if we're just full of hot air. We'll see. I think it's a really good idea though, and it could happen. And so that would mean it could happen all the time.
But the distance the distance would somehow reflect whether it's an early universe event or a later universe event.
Yeah, if we could build a more, well, the ELISA will be able to detect things in the early universe, although a different mass range than what LIGO will detect still. So we'll be able to get a bit of a handle on that as we make more detectors in several decades from now. Behind those guys is another guy.
What happens when two supermassive black holes merge together? I mean, like, do they go into each other?
Awesome question. They do go into each other. It's like the small black holes that merge. The two supermassive black holes will also merge and go into each other, but it will be messier because they're way bigger, and they probably have like a galaxy all around them, so there's going to be like billions of stars all around them too, and there's probably a bunch of like gas around, and so it'll probably be super awesome whenever that happens. I hope I see it. Yeah.
Could you have stellar mass black holes within a galaxy? More than one?
Oh yes, there are lots. There are tons. Any more?
Yeah, dude. So, like supermassive black hole can obviously swallow a planet, right?
Mm-hmm.
And the other question I wanted to ask you was, do they die? Like these things can die down or just disappear, like not become a black hole anymore?
That's something that Stephen Hawking has thought of called, there's something called Hawking radiation, where he predicts that black holes will evaporate. And this is really, really slow. takes a really long time. So it probably does happen. It's not something we can observe that at now for sure. Maybe someday we'll figure out a way to observe if he's right. He's probably right. He's super smart, but it's super slow. So I don't think about that a lot. Any more questions?
All right, thank you very much. We'll take the rest of the questions offline.
All right, I'll hang out for a bit.
Thank you again.
Thank you for coming.